welcome to everybody who's joining us today. I'm going to go ahead and turn things over to Robert. Go ahead, Robert, if you would like to introduce yourself.
All right, so welcome everyone. I'm an environmental health specialist. I've been involved with on-site wastewater, stormwater, wetlands, uh, all kinds of things for about 46 years. I was a regulator for 20 years and have been a consultant for 26 years. And so I'm going to be talking about a kind of a holistic approach to stormwater design. I won't get into a lot of the details of the 1200A and C and 1200 CN and Z, all those things. I think you'll be covering those in other presentations, but understand that permits are one of the main things that you're going to have to find who is the regulator in charge and follow the appropriate permits for those. So we'll talk in generalities and stop me if things don't make sense, but I'm going to start moving ahead as you can stop. But I've got a lot of slides to go through. What do you see now? Do you just see my screen or do you see a bunch of other stuff on there?
We
Can you
see your
hear me?
screen, Robert. You're good to go.
Okay. All right. Basically, the client is in charge of their property and often the least knowledgeable of all the folks involved, but they are in charge and they're the general manager unless someone else is appointed. So we have our firm and there's builders and engineers and surveyors and architects and plumbers and traffic engineers, soil scientists, all those kinds of things come to play. And ideally, we are going to work as a team to get the job done. Unfortunately, a lot of these projects have different silos of regulatory agencies at the local, state, and federal levels. But nevertheless, we can sort it out. The basics is let's prevent stormwater runoff rather than trying to treat it after the fact. And there's a bunch of best management practices that can be used. And we tend to use an approach that allows us to apply techniques as needed. So it's an adaptive management approach. One of the things about stormwater is you have these peak flows that are kind of unpredictable. You know what's happening in the spring, the winter and the spring, about exactly when and how bad is going to be something that you can prepare for, but can also be surprised. And that's where a lot of the energy that's involved comes in. So the stormwater, it's not just the moisture, but it's uh, the energy that is imparted on the site. So there are several things that can be used in somewhat of an order of preference, at least in Oregon. So one of them is to use the natural soil, maybe use some compost, and if necessary, amend the soils. Uh, some people think if you add sand, you're going to improve the ability of the soil to accept moisture, but that's not the case. Actually, sand is rock, does not actually help with the drainage. It's if you have sand and you've got a lot of space between the sand particles, then you've got some drainage. But if you think about adding sand to clay, you'd have clay with rock in it. So that doesn't work. So if you're looking at amending soils, you're really looking at compost or something like that. Natural soils, of course, are ideal in many cases, not always. There's a lot of techniques. Here's another order of preference is some kind of planter where you are capturing that uh, downfall, that rainfall or snow melt and treating it before it is discharged. That not only treats it in a series of planters, but also slows down the energy as it is returned to nature. Here's another one. We're talking about vegetation, various types of sedums, grasses, shrubs, trees, and the growing medium in order to do that. You may or may not have a green roof, but green roofs can be used effectively to capture and uh, treat that effluent before it gets to the downspout and further use. Excuse me. All right, so sorry I was interrupted a little bit. Anyway, so order of preference, another one is porous pavement, trying to uh, allow that that water to be returned at the site rather than hitting a pervious or impervious site. You have pervious pavement where the water will go down and be stored sometimes in voids and in between the surface and the natural subsurface. Sometimes you'll have rain gardens, retains water until it can evaporate. It's highly effective at treating the bubbles. There's typically no discharge, so your nutrients aren't leaving the site. And it's fairly used on fairly flat sites. Here's a local improvement district or low impact development swale, retains the water until it can evaporate, and getting high levels of treatment and retention of that water before it moves on. Use this on sloping sites, and often you'll have some check dams that will slow down that energy. We're talking again about energy, not just the water. There's some stormwater planters. You've got your roof, and that drains into a planter that's actually built into the house in some cases. That does a very good job. Typically, a lot of these are upflow planters. So you go in, rises up, is used by the plants, and then the excess is discharged beyond that. And of course, you've got to put these into some, not only look at the site, but how is this going to be built and maintained, and you draw up your plans so that the contractor can actually put it in the ground and do this in a manner that will allow things to be done. You're specifying what types of plants, what kind of slope, try to predict what the rainfall is going to be. And that upper right hand is a cross section of a planter where the roof drain comes down into the growing medium, and then you may have an overflow pipe that discharges once the water gets up to a high level. Rather than overflowing the box, it gets into that overflow pipe and is discharged. But mainly you're dealing with that energy and treating the contaminants. Here's another type of system where they've got infiltration through the soil. And in this case, your soil and your vegetation is designed to take up the majority, if not all, of the flow. In this case, there is also an added drain. So you've got your infiltration through the swale, but also a filtration and discharge point to drain the pipe, which may go on to another system. So you've got your plantings and you've got your slope, your existing grade. Sometimes you have mulch on there. It's all got to work together. Here's another kind of downfall or downspout treatment. So when you have your downspout goes into a sediment trap to catch those leaves and what have you. I do like some of those gutter devices that can keep the leaves from going into your sediment trap, as those will clog and they're often forgotten. So when you get all the gunk that falls into your gutters and down into your sediment trap, that in turn will go into your seepage trench and eventually clog things up. And there's a cross section there just showing the kinds of things you're looking at, the size and the application rate of the soil. You also have to figure out how wide, how deep, how long those components are. Here's another view where you've got downspouts going into the same kind of a sediment trap, and then you've got a dry well that is going to have holes in it that will allow that water to go into the soil. And of course, you need to take into account what is going to be affected downslope. So if you've got a neighbor downslope, you don't want to be adding that kind of water in an inopportune manner. And usually you're going to have fairly rapidly draining soils for something like this. And occasionally these are quite deep to get to a deeper strata of soil. Here's another swale, and bioswales work very well. Got to slow down the effluent, use it in the natural vegetation, and infiltrate and eventually move that soil down and out of the site. This is a little hard to see, but you're taking a look at some of the best management practices using that adaptive management. Certain things will be installed up front, and other things are just kind of ready to be installed if conditions warrant. So you're looking at water quality, drainage area, and local flooding, etc. So some of the things you know when you're doing your calculation, you know the size of your lot and what the slope is, the density, and a number of things like that. But you don't necessarily know exactly what's going to happen with your weather pattern. So you're trying to predict what the worst cases are going to be. Maybe your 10-year worst case would be the design phase for your time of concentration and your discharge rate. There's a number of factors you bring into play when you're looking at designing: coefficient of roughness, the soil, the slope. It's going to be different for graveled surfaces versus meadows versus pervious pavement. All those things have to be taken into account. Then there are a number of factors that are going to help you do the calculations. Of course, you've got your time of travel overland and length of the overland sheet flow if you're doing it that way, the roughness of the site that is receiving that flow, and your predicted rainfall intensity, inches per hour. And there are charts that can be used for that will be designed based on your particular geographic region. I won't try to go through the calculations here, but those calculations are published and you can certainly apply those. You're looking at those runoff coefficients and whether it's flat, rolling, or hilly, and putting that together. And sometimes they're looking for a 10-year interval or 25, 50, even 100 years, and that'll be taken into account. More calculations, and it would take us quite a while to go through all of this, but basically you're looking at the width and the depth and the square feet, the all those factors in order to predict how well that site is going to capture that flow and treat it on site. And typically you want to treat everything on site before you discharge off site. And even if you're not required to have a permit, which typically kicks in at 1 acre or more of disturbance, you can be fined for discharging off the site. So every site is required to maintain water quality and not cause problems for the neighbors. There's another method of putting in basically a bottomless sand filter for a bioswale that has a trench at the bottom. And of course, you're going to look at different hydrologic soil groups that will basically be based on the National Resource Conservation Service mapping and local maps based on what kind of soil and how fast it accepts flow. Denser soils are going to be slower at accepting flow. A lot of times you will be dealing with soils and you're going to do an infiltration test or perk test where you're pouring water in a hole and trying to determine exactly how well that is moving through the soil. Sometimes you'll use a device like an infiltrometer that will allow you to take those measurements more accurately. Here's a different type of infiltrometer where you're using these rings to calculate. So you want to saturate the outside ring as well as the inside ring in order to make your measurements. And then you're going to keep track of the data and make your measurements. That might be every 10 minutes. You might take a reading and try to determine how long it takes. In this case, it was time interval was 20 minutes. And how much did that water drop on the site? And you're looking at the average and the worst case. I'm wondering whether I have the latest presentation here. But are there any questions at this point?
There is one. It is, where is the runoff coefficient table from? Is it from a particular reference source?
Yeah, those are typically in your manuals for that particular jurisdiction. So the city of Portland, for instance, has a manual. Multnomah County. I would work with the local jurisdiction first. So I ran through that pretty quickly. Actually, I had a lot more that I was going to discuss.
Are there any more pointers that you have for anybody just
The
off the
main
system?
the main things I'm interested in or would like to get across is we have a lot of different things to take into account. And some of those, let me share this screen again if I can figure out how to do that.
You're still sharing the screen. You just need to put PowerPoint to present.
All right, what do you see now?
I see your screen. It's
Okay, great. All right, so there's a lot of things involved. There's wastewater, there's stormwater, there's wetlands, uh, the water itself, the foundations. You've got your clients. Um, you're going to start, typically, you're going to look at a lot of the mapped resources, the aerial photographs and topographic maps and soil maps and geologic maps, tax lot maps, all those kinds of things are going to come into play when you're trying to do planning on a site. So what is the community? What is the uh, nearby water bodies that you're going to be dealing with? And taking all that into account. So this is from the Natural Resource Conservation Service. Most of you should be familiar with this, but it will
um,
give you an idea. Go ahead.
Robert, really quick. Your screen isn't in present. We're still seeing all of your slides.
I'm sorry.
We're still seeing all of your slides. There's a little podium in the bottom right-hand corner of your PowerPoint screen. There you go.
Okay. Looks the same to me. Sorry. Anyway, so a lot of resources involved with evaluating a property before you even go out to the site. Some of those, trying to back this slide up a bit. Um, the Natural Resource Conservation Service maps soils. Now, these are not really site specific. They do a pretty good job of identifying what's there, but it's done on from aerial photographs and some site visits that have been done years ago. I am trying to get this to cooperate. It's not advancing. Apologize for that. How's that? Can you see me?
I can see you, but I cannot see your PowerPoint.
Swell.
You should just need to hit the share button on Zoom, the green button, and then I'll bring it up again.
Well, it'd be great if I could find it. There's the green button. How's that?
Can you make that? There you go. Perfect.
Okay. So as I was mentioning, you're going to be looking at a lot of resources, your aerial photographs, topographic maps, soil maps, and these are published maps. Ideally, you would actually go to the site, have your topography done and soil work done. Can't rely totally on these kinds of maps, so they give you a pretty good idea what to expect before going out to a site. And the Natural Resource Conservation Service has pretty good maps, and they can tell you what kinds of soils to expect and major bodies of water that may or may not still be there. And then there's a wealth of information on each of those soil types, and there's a lot of engineering properties that can be brought to bear on that. And here's something from the University of California, Davis, that has taken a lot of that same information and added to it. And of course, we do have to go to the site and start digging, but before you dig, make sure you know, especially if you're digging with a backhoe, but even a hand digging can cause some problems. So this can cause severe injuries. So you do go to the site and you're looking at the vegetation, the lay of the land. If you're looking at wetlands, your upper left is very shallow soil evaluation. You're really only going down about 18 inches to identify wetland soils. And a lot of times, lower left is hand augering to determine. We can go down a few feet that way, depending on the soil type. But then you may also be using a backhoe to dig and see whether or not you've got really good soils there. We're looking for uniformity of the soil, and there's some things we'll get into. So we're looking at the porosity. Are there channels in the soil from roots and worms, etc., beetles? And do you see evidence of saturation? We're looking at the texture of the soil, which just talks about the amount of sand, silt, and clay, and that gives you a pretty good idea that heavily clayed areas are going to be, they will accept a lot of water because they do have a lot of uh, void space, but then up to a point, and then they don't release the soil very well. So a medium soil like a loam, now medium meaning it's closer to the sand and silt rather than clay. So clay loam, sandy clay loam, sandy loam, and silt loam. Those are those are pretty good soils for most purposes. You also want to look at the structure of the soil. You know, single grains that are rapid, like sand and gravel, but the water may move too quickly through it. Blocky or prismatic soils are usually better. They're moderate in the amount of water that moves through them. And then when you're dealing with clayey soil, clay is kind of like shingles on a roof. They're flat particles that kind of impede the flow. You can actually be massive, what's called massive, and it'll accept some water, but it just won't allow things to that water to move through effectively. So when you're looking at test pits, you're looking to see, you know, just how uh, the soil, how the structure, the color. So you're looking at nice, uniform, even color is better than something that has abrupt changes to it. So this is a kind of a medium color, kind of reddish brown soil would be considered good soil for many purposes. Wetlands, you're going to be involved with wetlands. You may be draining your stormwater into a wetland. That may be acceptable, but there are some restrictions on use and impact. So if you are trying to alter wetlands in the process, then you've got some permits there you've got to deal with. So you're looking at here, you've got soils that are a gray soil. It may be that you would run into soil that was a natural soil was ash, for instance. It may be naturally gray, but often the soil that has been wet and dried out and wet, dried out, that iron will be removed from the soil. And so you will sometimes have a soil that indicates that it's often wet. Here's another type of soil where the top, about half of that test pit, the top, say 12 inches, is very good soil, but then you start getting to and orange and gray models, or what they call redoxamorphic features, which would be rust spots, redoxamorphic meaning redox and well, reduction and oxidation of the soil. So you've got your natural iron in the soil. If it's evenly dispersed, it will be a nice uniform color. But if the iron gets wet, then it'll clump together in rust spots and gray spots where the soil is reduced. So it may not be suitable. So we've got some soil there, and then it gets into saturated conditions. If you go out there in August, you're not going to see the water. You're looking at the land, the lay of the land. Now, septic drain fields, you need to avoid the low spots, but it may be very good for stormwater drainage. And you can't always tell during the dry weather. And a poorly drained site, you're going to have to take that into account when you're dealing. So when they dug these pits, they were probably dry. And then you're dealing with removal fill permits if you have to alter the wetlands. So, and you're really trying to avoid impacts or minimize the impacts and then mitigate for those impacts, but then try to avoid, or you'd have to either create wetlands elsewhere, pay for a wetland mitigation bank, or not build on that particular area. You can avoid, minimize, and mitigate. And not only do you have to look at the site and the soil, but can you actually get your equipment there? Can you navigate to the site? If it's too steep, can you actually build it? And of course, when you're on a steep slope, then that water moving down slope can cause erosion. So you need to be able to slow that down with check dams or infiltration trenches. Natural vegetation is another thing that you want to keep in place as much as possible. So we're also looking at the site and what has happened to the site from drainage. You're looking at some geologic maps. You're looking at what has been eroded near the streams. The site on the upper right, it used to be a stream that was 30 feet away, and now it's 10 feet away from the site. The one on the lower left, that lot on the Oregon coast used to be 3 blocks back from the Pacific Ocean. Now it's a viewpoint with about 4 feet to the Pacific Ocean. It's been a year or so since I looked at that site, so who knows? Maybe it's not even there anymore. You can see where the trees have fallen that were once there. And the lower right, there's some erosion control measures, the sediment fence, and they're showing some straw bales. It's not really as common to use straw bales as once was, but there are various techniques for erosion control. And so you're looking at the site, the horizontal separations from wells and water lines and drain fields, the stormwater drainage, surface water, and of course, property lines and buildings. You can't be causing problems for the structure or other components like the drain field. And then, of course, the vertical separation has to do with the depth to the water table. Do you have a high water table? Do you have dense soil or bedrock, or soil that's so coarse that water moves through it quickly? And then you got to look at the quantity and quality of the existing and proposed flow. What's currently going on, and what are you proposing to do that may cause problems? A lot of problems or sites were not problematic for years and years until somebody builds upslope and you've got an issue. It's nice to know what's going on with the roots. Most of the vegetation is in the top few inches. And of course, nitrogen can be an issue. Nice to understand that biology. When you look at the actual biology, you're looking at the top 16 inches having almost all of the actual biologic uh, vegetate or biologic organisms, the worms and the bacteria and the roots and all that. So if you bypass that top 16 inches, now you have less biology to actually help you treat that discharged material. And then we're getting into this fact of the peak flows are going to be a major factor when you start looking at energy and how that could affect the flow. So here's another diagram. So on this site, you may put your drain field on that site to the to the right. And because that's a convex site, the water will tend to spread out and move down slope, whereas the site to the lower left is more of a concave site where that concentrates your flow. So that may be an acceptable place to put your stormwater flow, assuming you can do that in a manner that you're not going to erode the soil. So you'd have your bioswales and your check dams and so forth in that area. All of what you're trying to do is visualize the subsurface environment. And if you're just thinking about one part of it, such as the septic tank, uh, you really need to look at other things like where is the stormwater drainage going, and vice versa. If you're putting together a plan for stormwater, where is that going? Are you going to be saturating the septic drain field, or having that water flow into the public sewer? Nowadays, the public sewers, the combined sewer overflow is typically not allowed. It's over the years has been not such a problem, but as you add more and more folks, more and more outdated infrastructure, public sewers, and that the roof drains can and storm drains, et cetera, can be problematic. Getting into that compost, I've already been through some of this. I apologize that I had an older version of the presentation there, but you're dealing with various types of uh, best management practices. All of these are good for some sites and not for other. Of course, elevations, you really need to understand the elevations of the sites you're dealing with and how everything is going to work together, and try to spread that out over the slope instead of just going downhill as fast as you can get it. You want to get it spread out. And something like this, as I mentioned, you can possibly put in a dry well if allowed, and if that isn't going to cause problems for downslope neighbors or to the groundwater. So that could also be a underground injection control well permit. We talked about the calculations, some of the resources for doing those calculations, and typically you're dealing with a manual that is specific to your area and your jurisdiction. But the general calculations are going to be similar. The amount of rainfall is going to be quite a bit different, and the type of soil you have. Some areas are very sandy, other areas are are very dense, a lot of clay, a lot of water. So there's a big difference between the Willamette Valley and Eastern Oregon high desert. And when you dig these holes, you need to make sure that you scarify the sides. Typically, we tend to use the infiltrometers. The hydrology, you're going to be looking at evidence for the water table before you start any digging. So you'll see on the left, you've got obvious water and wetland vegetation on the fringes. In the middle, you've got some pockets there, some coloration of the soil. And then on the right side, you may not have any water, but you may have cracking of the soil that indicates it was wet and dried out. And sometimes those cracks are quite large in the case of a very clayey soil like a vertisol. Hydric soils, these are also mapped by the Natural Resource Conservation Service, and those same kinds of maps are also available on some county websites where they will identify what's likely to be hydric soils. Again, you're going to be looking at those actual look at the maps, but you have to go to the site and determine what's really there. And just a couple of inches can make a difference between approval and denial on some of these soils. You're looking for changes in soil chemistry and color, and typically iron is the main one that we're looking at. Manganese can also be an indicator. Manganese can create black stains on surface. Sometimes you'll see some charcoal that's from a fire, for instance, but that's more of a three-dimensional thing rather than manganese, which would be a coating. Iron is ubiquitous, is in most places, and it will turn orange when it rusts or oxidizes, and turn grayer when it is reduced. And we're looking at some of the conditions. If you have a gray, dark gray, or dark soils, that may be from rotting vegetation, and rotting soil. You may be looking for some sulfur smell when you're digging, that kind of thing. And then when the lower uh, sample, you're looking at, it's kind of hard to see unless you're used to it, but there's orange and gray. So you're looking at little spots of both oxidized or orangey color, and also gray around the oxidized soil, which is reduced soil. And then you don't just call it, well, that looks kind of gray, that you got to use a standard, which in this case is a Munsell soil chart, to actually go in and say, well, that's a 10YR33, and the soil may be a 10YR21, etc. And that'll tell someone else what you actually saw. And there are some other things like root penetration and the structure of the soil that you're looking at. And then the vegetation, of course, you're looking to see, there's a range of wetland plants from the obligate wetlands. They must be wetlands or else they won't survive, to facultative wetlands that like to be wet, but they can stand to be dry for a while. The facultative can go in the middle. The facultative uplands prefer to be dry, but they can stand to be wet. And then the upland plants are obligate upland plants. And of course, our company, we do a lot of these different things. And try to have that holistic approach that everyone should have when you're trying to deal with property. Any additional questions at this point?
We do. We have a few questions while we still have some time. Elizabeth is wondering if there are any case studies that you have that would be relevant.
Yes, there are a number of studies like that. If you wanted to email me, I can provide some of those.
Perfect. There's another question from Nico. How do you find multiple years worth of specific precipitation data? Do you combine this with site-specific contour data?
Could you say that again?
Yes. How do you find multiple years worth of specific precipitation, goodness, data? Do you combine this with site-specific contour data?
Right. Yes. So you're going to look at the averages. You're going to look at patterns over the years, and depending on what your requirement is, you're going to be looking at 10 years or maybe even 100-year uh, patterns. So those are published. You go to the various sources, including the Weather Service, and sometimes we use Weather Underground and a number of sources like that. And of course, the wetland agencies that are dealing with your particular area, and trying to paint a picture of what's the worst case and is it likely to occur? How rapidly is it? I mean, you can't predict or you can't prevent serious 100-year flood zones from occurring and not have any impact, but you're trying to minimize those. And yeah, so you're looking at that data from various sources and the mapping the worst case and the average, and uh, trying to determine what is expected.
Perfect. And then I have one more question. Can you tell us about the O&M costs for various LID options? Which ones do you find the most cost effective?
Yeah, so O&M has been kind of hit and miss. A lot of places they indicate that they will require monitoring, and then if they don't require monitoring, then there's not much of a consequence. But typically, you want to design so that you don't have to replace the plants, but that's exactly what you need to do. You going in and identify whether or not the silt fences, which are usually temporary. Uh, what I like, amongst other things, would be compost berms and kind of build that into the site. You want to have a structural design that is going to last. Natural veget you keep your natural vegetation, and then you've got some weirs and what have you. You can build into your structure to allow that effluent to be caught and distributed uh, evenly throughout the site as opposed to channelized. So sometimes you'll have some grade boards that have notches in them that will allow that water to be caught in basically a trench that overflows, and then you've got notches there that will allow that to be spread out. The compost berms are things you can put a lot of compost down in the downslope area instead of or in addition to the sediment fences. And then the sediment fences go away, but the compost berm can be essentially used to grow vegetation and allow that compost to be a long-lasting infiltrative, not really a barrier, but a manner of allowing flow to continue down slow, but in a slower manner. Other things like catch basins or the check dams and slopes, those last a long time. You still need to look and see whether or not they're adequate. Those things work pretty well if you do them right. Are you finding that there are specific O&M requirements that are difficult to maintain?
The question didn't specify.
Say again?
The question didn't specify which ones.
Okay. All right.
All right, well, I think that brings us to the end of our workshop. Thank you, Robert. That was really great. Learned a lot for sure. Thank you, everybody, for joining us for Stormwater Awareness Week. If you missed any part of this workshop or would like to view it later, this session has been recorded and it should be available up on stormwaterawareness.org within the next 24 to 48 hours. So yeah, thank you for joining us. There are still a couple more workshops today. One at 3 o'clock for the Russell application for notice of termination. So you still have the opportunity to go ahead and sign up for those if you haven't already. And we still have the rest of the week of workshops as well. So thank you everybody for coming out.